Hello, my name is Mattia Sabatini and I will present our virtual poster entitled Improving Copernicus Level 4 SST Regional Products with CIMR Observations. Within the context of the Copernicus Marine Service, the National Research Council of Italy provides two SST products for the Mediterranean Sea, a merged multisensor Level 3 SST and an optimally interpolated gap-free Level 4 SST. These products are based on satellite observations from infrared sensors only. Infrared sensors have the advantage to retrieve SST at high resolution, but only in clear sky conditions. Microwave sensors, on the other side, are able to retrieve SST even in presence of non-precipitating clouds, although the spatial resolution is coarse. The figures show a comparison between two daily SST maps derived from an infrared sensor on the left, SLSTR, and a microwave one on the right, AMSR2. Given that CIMR is expected to retrieve SST at a resolution lower or equal than 15 kilometers, we did a preliminary assessment of the impact that this instrument could have on the Mediterranean SST products. The following work is based on the Copernicus Mediterranean Sea physical analysis and forecast model outputs and relies on the optimal interpolation algorithm from the SST processing chains of CNR. In a first run, the optimal interpolation algorithm ingests synthetic infrared SST generated from the Copernicus model. In a second run, the optimal interpolation algorithm ingests synthetic infrared and CIMR SST. The level 4 SST resulting from these two rounds are then validated against the model SST. To generate the synthetic infrared SST, we applied the Copernicus Level 3S cloud mask to the model SST, and finally we added the radiometric noise. The figure shows an example of this synthetic data. The materials used for the generation of the synthetic CIMR SST are coverage data derived from an ESA tool, precipitation data from the ISMAR dataset, and the theoretical SST retrieval error from Kilic et al. First, the model SST is regridded in order to mimic the expected CIMR SST resolution. Then we applied cost, coverage, and rain masks to the data. And finally, we added noise. Concerning the coverage mask, for now we excluded diurnal passages to avoid diurnal warming effects. Merging of infrared and CIMR SST is performed remapping CIMR data to the infrared grid, which is the one used for the optimal interpolation, and including each microwave observation once. The final result is shown in the bottom figure, with the magnified area showing in detail the gaps in CIMR data due to the merging. The preliminary results we obtained are shown in the following slides. Going from left to right, we can see here the optimal interpolated SST using only infrared data as input, using combined infrared and CIMR, and the reference model SST. There seems to be more consistency with reference SST when CIMR is included in the optimal interpolation algorithm. This is the histogram of the January mean error, that is the difference between optimal interpolated and reference SST. The blue histogram is the one obtained including CIMR in the algorithm and provides a better error distribution compared to the infrared-only red histogram. This figure shows the change in root mean square error when CIMR is added as optimal interpolation input. The blue color represents all areas where root mean square error decreases, leading to an improvement in the analysis. This slide concludes the presentation. Being a preliminary work, there are some aspects we are currently not accounting for that could be included in future activities. For example, the radio frequency interference effects. Thank you for your attention.